Hello and welcome everybody to our lecture today on basics on solar refrigerators and freezers. My name is Victor and I'm going to give you an overview of conventional solar refrigerators, but also how to use these conventional refrigerators, for example, for ice makers as an example of productive use applications. And later on also a very interesting product which is a battery-free refrigerator that is powered directly by PV panels without using batteries, and including ice storage integrated in the walls of the refrigerator. This we will see at the end. First of all, we start with the conventional solar refrigerator. I would like to give you here an overview of the different components that you have. Of course, first of all, the refrigerator, which could be also an AC refrigerator, a conventional refrigerator that you can connect to the grid. But it is preferable to have a DC refrigerator that is running at 12 or 24 volts, which will be the voltage of your batteries, and then you don't need to use an inverter. That is normally quite expensive for refrigerators because of the peak current that we were seeing in the previous lecture. And then, as you can see here, if this is a refrigerator that needs to use batteries, then you have your batteries in series or parallel depending on the voltage you want to have for your refrigerator. A charge controller that might have an MPPT tracker or not. This is a detail of solar components. So with an MPPT tracker, you save a little bit of PV panels, but at current prices of PV panels, this is not crucial for such a small system. So I would recommend to use conventional charge controllers, and here the PV panels. So we are going to go through how they work and also how to design them, how much PV panels we need, and batteries, depending also how intensive we use the solar refrigerators. Normally, when you are dealing with a solar refrigerator, then you get such a consumption information that is, of course, depending a lot on the ambient temperature, but also on the interior temperature, on the temperature of the inner chamber. And as we saw in other lectures, you can see here how a heat pump is integrated in the solar refrigerator. So you have the compressor here inside, the condenser coils, which are normally the black coils that you can see on the back of the refrigerator and that get warm, and then the expansion device that is usually a capillary tube, and the evaporator coils that are here integrated into the wall of the refrigerator. If it's a defrost refrigerator, then this will be a heat exchanger to produce cold air. But in conventional refrigerators, you find the evaporator coil, whether here on top or here integrated in the walls. Then you need, of course, a temperature sensor to start and stop the compressor when the set point temperature has been achieved. And this set point temperature is, of course, decided by the user, and depending on that, you have here, as I said, different energy consumption. If you go, for example, to minus 20 degrees and an ambient temperature of 40 degrees, then you see a huge difference than when you are using it just to cool down the products at 3 degrees and at 25 degrees ambient temperature. And I have to say, this information is normally only related to the thermal losses. So this information or this energy consumption take in consideration that the refrigerator remains closed So it is just to keep the food cold, or just to keep this temperature. And this is very important when you are designing a solar refrigerator, because if you just take this information, as soon as the user is, for example, cooling drinks or other stuff, then the energy consumption will increase, and the batteries will be lower as expected. And I'm going to give you an overview of this over the lecture. But how can we, for example, do our own testing on solar refrigerators? How can we know which is the energy consumption of a 13 refrigerator depending on the ambient consumption and the cooling load? This means how the user is using the refrigerator. So I would like to give you an overview of our experimental testing bench that we have at the institute. And it contains two parts. So the first one you see here, it is just a PC with a MATLAB model that is running on Meteornorm weather data, and this weather model is able to know what is the PV radiation or the solar radiation, and then convert it into PV power, and can emulate this PV power with help of a PV simulator. So we emulate the actual electrical power coming from the PV panels, and at the same time, here in the climate chamber, we simulate the ambient temperature. And it is important that this happens at the same time, because during the day you have a lot of energy available, so the batteries are high, have a high SOC, state of charge, I mean, but at the same time you have a high ambient temperature, so the efficiency of your refrigerator is lower, the COP, the coefficient of operation, and the thermal losses are also higher. So this compensates somehow, and it is important to measure both at the same time, that you emulate your PV power and your ambient temperature at the same time. I have a video here for you, and in this video you can have a look how the solar cooling test bench it is. You can select your location and which day of the year, and here you see the PV curve that is simulated. So you can enter, okay, I have a 300 watt peak or 400 watt peak, and then the PV power is simulated. And here inside the climate chamber we have the batteries and charge controller, we have the refrigerator, the ambient temperature is simulated by a heater with a thermostat, and here you can see refrigerator, that in this case was used as an ice maker with the temperature sensors and with the energy consumption. So we can log this information, consumption and temperatures at the same time, and this helps us to verify what is the energy consumption depending on different parameters, so weather conditions, how the system is used, if we are putting a lot of cooling load or not, if we are opening the door often or not. So for example, here you can see an experiment we have done here in the climate chamber, where we have tested different cooling behavior depending on the cooling method. So if you are just putting, for example, here in this case, water bottles in natural convection, so you don't have any fan, then you will have this cooling curve you see here in red. So it takes from 30 degrees to 4 degrees, what is here the set point temperature. It takes quite a long time, 10 hours. So you can see the cooling behavior in a refrigerator might be important, depending on what you want to do with the refrigerator. And just have a look to the difference when you just install a small fan in the refrigerator. Will be here the blue curve. So you see the cooling curve is happening much faster. In around 4 hours we are around our goal temperature. And there is also a possibility, for example, if you need your products to be cooled down very quickly, you can enter a water bath inside the refrigerator, and then you will have very fast cooling speed, very fast cooling curve here. You see it decreases very fastly to the water temperature, and then it takes a while because it has to cool down also the water. This is just to give you an overview on how important the cooling behavior is in a refrigerator, and this is also important for the consumption, because if the cooling is happening slowly, then the energy consumption is also distributed along this period. If the cooling is happening quicker, then the energy consumption is concentrated here in the first hour. So not only how much cooling demand you have, so how much food or drink you are entering a refrigerator, but also how it is the heat transfer inside the refrigerator is important for the energy consumption. This is a detail, but I thought it's important to see. And here I would like to show you the effect of cooling down in the refrigerator different amount, in this case of water. So we did here a test with 3, 6, 12 and 18 liter of water, and here you can see the cooling curve was actually very similar. Why is this? Because the compressor is adapting. If you are putting a lot of products at the same time, then the compressor will be working more time. We call this a duty cycle. And if you are putting less amount of water or food, then the compressor will start, stop, and this is also affecting the consumption. But you see here with 18 liter, with this latest curve here, it is already affected a little bit, the cooling curve, and this is because we have achieved the maximum power of the refrigerator. So the refrigerator is not able to cool down more than this. If you put more than this, then the cooling curve will be always slower, because the power of the refrigerator, the power of the compressor is not enough to cool down the product at the speed that we expect. So let's have a look here to the energy consumption. We have here, you see here 2 bottles of water, so 3 liters up to 18 liters. So you see here the energy consumption is low over the time if you have less amount of product, and quite high if you have higher amount of product. And you see here what I mentioned before, we were already at the maximum power of the refrigerator, in this case 100 watts. And then if the compressor is here working for 3 hours at full power, so to say, the whole time without having any start and stop. Yeah, and once the product has been cooled down, then you see the energy consumption is all increasing quite slowly, and this is because of the thermal losses. So in the energy consumption of the refrigerator, you have always a portion of cooling power that is delivered to the product that you are putting inside, and another part is the thermal losses that you have continuously there, and that depend only on the ambient temperature. Okay. And now let's have also a look to the influence on the ambient temperature, on the cooling curve, and later on in the energy consumption. So you see here we are putting also here water bottles inside the refrigerator at 25 degrees ambient temperature in black, and in red at 35 degrees ambient temperature. So you see the cooling curve is almost the same, because the compressor is then reacting to this. I mean, you see here the air temperature inside the refrigerator, so it's just set at 4 degrees. And because the air temperature inside the refrigerator is the same, then the cooling curve is also the same. But the consumption is affected. And you can actually see it here, the red one, or perhaps you cannot see it here so well, but you can see it here in this curve better. The energy consumption is much higher here in the case of 35 degrees compared to the 25 degrees. And you see also here the gradient is also higher in this curve, so the thermal losses are of course also higher. But not only the thermal losses, also the energy consumed to cool down the product. And this is because the coefficient of operation, as you heard from the other lecture, the COP, the coefficient of operation of a refrigerator and in general of a cooling machine, decrease considerably by increasing the ambient temperature. So you see here, to do exactly the same, to cool down the same amount of water in a refrigerator, the energy consumption is here around 30% more if you have 35 degrees ambient temperature instead of 25 degrees. We are ready to have a look to the equations behind the calculation of the cooling load and the thermal losses. So as we mentioned, we have a certain amount of energy that is needed to cool down the product. We call this cooling load. And we have from the other side also thermal losses. Both amount of energy, of cold energy, need to be delivered by the heat pump, by the refrigeration machine. And this we call the cooling power. That is then through the evaporator coming to the inner chamber, so to say, and this is delivered by the heat pump through an electrical power that is consumed by the compressor. And if you remember, the cooling power is equal to the electrical power times the COP. So depending how high is the COP, then better we will pump the heat, so to say, and have a better efficiency. And here you see the equation to calculate the thermal losses. So we have seen this equation also in the other lectures, where you have the area and the heat transfer coefficient of your insulation, and then the delta T, the difference between ambient temperature and the temperature inside the refrigerator. This is easy. And then you have also the cooling load. The cooling load depends on the amount of product that you are putting inside, but also on the surface of this product. I don't want to go here in detail. You will see this in the lecture of cold rooms in a better detail. But at the end of the day, you can see here the equation that depends on the heat capacity of the product, on the volume of the product. If you want to go into detail on that. And then you have the sum here of both powers, thermal losses and cooling load, and then multiplied by the COP is your electrical energy consumption, so to say. And you can then calculate actually the cooling consumption that you are going to have depending on the amount of load that you are entering the refrigerator and the ambient temperature. So you can see here an example of our measurements here in gray and our simulation. So you can see with these simple equations that you see here in this slide, you can easily have a model that is quite reliable to calculate your own energy consumption. And I think this is important if you want to get into detail, because if you don't have well estimated the energy consumption of your refrigerator, once you want to do the design of the PV panels and the batteries, you will do additional mistakes, so to say. You will accumulate in an error. And you know, to design the PV panels and the batteries has also a variable parameter, which is the weather conditions. So the first step here is to know well your product and know well how this product is going to be used, so that you have the energy consumption, which will be also vary by days and depending how you program this. You can also see here also the COP that was measured in the experiments we did. 25 degrees 1.9 COP and 35 degrees 1.5. And now we want to integrate these equations into a solar simulation, because the refrigerator will be every day at a different ambient temperature, and this depends on weather data. And the PV panels will have more or less energy available depending on how sunny the day is. So if you want to simulate and to design a solar refrigerator, at some time you need to consider the energy consumption and the solar energy availability all over the year. And for this, you can, for example, select a typical weather data from Meteonorm, which is a mean values of the last 10 years. And this can help you to estimate well the design of the refrigerator. So let's have a look how this can be done. We had a look before to the real condition measurements at different ambient temperatures. So at the end of the day, you have a refrigerator model. It's based on the equations I have shown you before, and these equations are somehow calibrated with the experiments that you have done. So you can, based on the experiment, say, okay, I thought the insulation will be so good, but actually based on the measurements, it is like this. Or I thought I will have such a COP, but based on the experiments, I have seen that the COP at this ambient temperature is so much or so much. And then you can update your refrigerator model. Once you have the refrigerator model, you need the weather data. As I said, in the best case, typical weather data. So perhaps not taking just a 1 year or 1 month that somebody has measured, because this might be different to what is usually happening at this location. So typical weather data would help here, and a PV simulation model that I'm not going to go into detail, but at the end of the day, it's just a model that translates you the solar radiation to PV power, so to say, or to a current voltage curve. Then, of course, it's important to consider the cooling scenario. And as cooling scenario, we understand the refrigeration load and exchange times. So how many drinks, how much food are you entering at the refrigerator, at which time is this happening in the morning, is this happening in the middle of the day? This will have an influence. You can imagine if you want to use the refrigerator to produce ice or to cool down milk in the very early in the morning, this will means you have a high cooling load at the beginning of the day where the batteries are empty. So this will affect also the design of your refrigerator. So not only the amount of food or drinks during the day, but also the time, the exchange times. Then the location, I mean here not the place where the refrigerator is, but more important is to know if the refrigerator is outdoors or indoors. It can have advantages and disadvantages depending on the difference between your ambient temperature and your room temperature. But I will say if your refrigerator is in the shadow in a room that is not so hot, then it will have an advantage compared on having the refrigerator outside where the ambient temperature will be higher, and then the COP will be lower, the energy consumption will be higher, and so on. So that's also important to specify in a model. The container volume, especially because we saw before in the cooling behavior that this affect the cooling speed. So then it will affect your energy consumption, not the total of energy consumption, but how this energy consumption is distributed over the day. And the cooling method here, as we said, natural convention will be if you don't do any modification to the refrigerator, if you are not having a fan or something like that. Okay, let's go ahead. Now we can actually know what's going on with the refrigerator all over the year, and we could say, okay, now I do a simulation with so much PV panels and so much batteries and see what's happened, if I'm happy or not with the design. And by doing this, so to say, a try and error, you could optimize what is the better combination between PV and batteries for these 13 locations that you have selected. Of course, I mentioned before outdoors and indoors, but of course also the solar location. It is very important here. If it's in the tropics or subtropic, makes a big difference when you are designing. Okay, so let's have a look how such a simulation would look like. But as you saw, you have a refrigerator model, and then you test different combinations and PV and batteries, and then you take the one that you like most. And if you are able to make an algorithm of this, then the selection will be, of course, automatically. Now it's getting interesting. We have here already our first simulation, and you can see here in this diagram the solar irradiation of the location we have selected here, Havana, Cuba. So you see here, you can observe here how the rainy season is here with high solar fluctuations. You can see also, so to say here, summer and the winter, and then the days or the periods with lowest radiation here in November and December. And here on the right upper corner, you see the ambient temperature, the location. So you see the fluctuations between day and night, and how also the difference is between summer and winter. And the refrigerator is connected to a solar system with 120 watt peak and a battery of 1500 watt hour. This was the optimization we have done for this location for a refrigerator that has to cool down 5 liter water per day from 30 degrees to the set point temperature 4 degrees. Okay, so we have designed the refrigerator and we are simulating what is happening now all over the year, and this you see in the bottom. Here on the left side you see the energy consumption. So you see in summer is consuming a little bit more than in winter, and it depends actually on the ambient temperature only, because we are simulating always the same amount of water to be cooled down. And on the right bottom you see the state of charge of the batteries, the SOC of the batteries after 5 years of operation. So you see the batteries are not getting any more to 100% because over the time they are losing capacity. They have a kind of aging effect here that we can observe. You see how this decrease, and this is also something we have considered in our simulation model, because we know from the battery manufacturer what are the aging effects that we expect if we use the battery like this or like that. So this depends also on the depth of death, so how much we are, or how much we are discharging the batteries. So you see here we have just a couple of days during the rainy season where you can see that the battery SOC is going down to 60%, which is here not critical at all. After 5 years, the batteries are still healthy, I will say, with a high capacity, remaining capacity of around 90%. The customer is always happy. You see here that the air temperature inside the refrigerator was over the whole year at 4 degrees. So the customer is also happy. The refrigerator is doing what is expected to do. And now we are changing something. The user here is starting to cool down 15 liters of water per day. So not 5, but 15. So he's using now, he or she is using now the refrigerator in a different way that was not thought at the beginning. So it has been a change on the way how the operator, the user is operating with the refrigerator. So you see here, what can we see here? For example, the energy consumption is as double as much as it was before. Yeah, and this is not coming from the thermal losses, which remain the same. This is coming from the cooling load. You have 3 times more cooling load, more drinks, warm drinks that are enter the refrigerator, and then the consumption is much higher. And what is happening, the battery SOC is some days going down to 20%. So the charge controller is shutting down the system here at this case, and then the refrigerator cannot maintain the temperature. So you see here the temperatures of the refrigerator are going up to the ambient temperature. So here in a great amount of days the user is not going to be happy. The drinks are going to be warm, and the batteries will be destroyed after 5 years. You see the remaining capacity is only here 65%. So you have to exchange the battery. So the user is not happy, then the batteries you have to replace. So this is due a bad design of the system, because the system was designed for 5 liters per day and not for 15 liters per day. So this is very interesting to see how this can affect the design. And what I mentioned before, here the battery lifetime depends a lot on the DOD, which is the depth of discharge, which is actually telling us, okay, how much are you discharging the battery per day or per cycle. So a depth of discharge of 100% means we are discharging every day the battery 100%. Yeah, we are going from 100 to 0. Or perhaps you have 50%, so you are going from 100 to 50, or from 90 to 40, or 30% you are going from 100 to 70, for example. And depending how much or how less you are discharging your battery per cycle, the longest the lifetime of the battery will be. And this is determined by the cycle number. So if we are, for example, discharging only 30% of the battery every day, we can have 1,200 cycles, which are around 4 years. And if we discharge the battery 100% by cycle, then it won't last even 1 year. Yeah, you see how the capacity decrease actually. And this will be then the end of life of the battery. So this is also important. That's why we consider this in our simulations models, because then you can figure out what is better, to have a bigger battery that lasts for longer, or to have a smaller battery that you have to replace more often, but you save money, yeah, but at the beginning. So this is also important for the design of a solar refrigerator. You have to figure out also and compare different battery technologies and how is the lifetime of them. Now we can go here a little bit further in the design of a solar refrigerator, because we mentioned before, okay, the cooling load is actually dominating the energy consumption, right? So you can see here the same refrigerator we had before. If you remember, at Havana Outdoors, and we could say here, if it's working in idle, this means we are not cooling down any drinks. It's just about keeping the food cold or the drink cold. Then you can see here in the line the different combinations of PV power, I mean the amount of PV panels in watt peak, and the battery capacity. If you remember from the case before, we were having 1.5 kilowatt hour and 150 watt peak, so we were here at this point, and then you can see, okay, we were fine, we are over idle and probably also over 5 liter per day, and here's the curve of 10 liter per day, yeah, and here's the one for 20 liter per day. And the numbers you see here are the cost of the system, yeah. That of course depend on the price you pay for the PV panels and for the batteries. This is just our estimations here. So you see, if you have refrigerator at this location that is working in idle, then you can pay 1,000 euros, yeah, and this will work, yeah, and any combination here will work. I mean, you can have a lot of PV and less batteries, or less PV panels and more batteries, you see. So I think this diagram is very interesting because it's giving you a feeling for your design, and different combinations of PV and batteries work for that, but there is always an optimum. The optimum is always, so to say, there where the combination is the cheapest one, so to say. So you see here, all of them here at 10 liter per day will work, but this one is the cheapest one, yeah. So that's why we like to design here. And if the user says no, I want to cool down 20 liters per day, then we will say, okay, no problem, don't buy, I mean, we will install not 150 watt peak and 1.5 kilowatt hours of battery, we will install 200 watt peak and 2.5 kilowatt hour of battery capacity. And then you see the price is changing from 1,300 euros to 1,600 euros. So you pay 300 euros more for the refrigerator to be used for 20 liter per day, but the customer will be happy. So you see, it is very important here to design it well, because the amount of cost that we have is it not much higher, but the user satisfaction will be then fine if we design it accordingly. So in the case of solar refrigerators, the cooling demand it's very important. How the refrigerator is used is very important. This is different than, for example, for your refrigerator connected to the grid that you might have at home. There you don't care if you put more food, then the consumption will be higher, but you don't realize that, or you realize it only when you have to pay the bill. But in a solar refrigerator, this is crucial, yeah. Otherwise, the customers are not satisfied, and they pay already a good amount of money, and they need to be satisfied and have the feeling they have always energy when they need it, yeah. Now we can have also a look to the sensibility of the set point temperature, because you don't need to run the refrigerator at 4 degrees. Perhaps your food will be also fine at 8 degrees, for example. So let's have a look how this is influencing the design of the refrigerator. So we said 4 degrees. If you want to keep the temperature at 4 degrees, then you have to design like this. This is now for 10 liter per day, so it's comparable to the case before. So you see here this curve. But if the user say, okay, I don't want to cool down my drinks, my 10 liter water or whatever, I don't want to cool it down to 4 degrees, for me it's fine to have it at 8 degrees. So you see here the curve at 8 degrees, and we go from a cost of 1,300 to 1,000, almost 1,200. So you save here 100 euros in the amount of PVs and batteries that you need to install. And if you go to 12 degrees, then it decreases even higher. So I have written here 32 euros per degree, and you save on the design of the solar system. So the final temperature, the set point temperature, is also important here in the design of the refrigerator, as you have seen. And most of you are probably also expecting the sensibility of the location, right? So it's not the same to be here in the case in a country or in another one, to have a subtropical weather or a tropical weather, or to be in the mountains, for example. This affects also on the design. So if you are in the mountains, then the ambient temperature is lower, so your batteries and PV panels can be also smaller because the energy consumption is lower to do the same. Yeah. So here I wanted to bring you 3 different scenarios, yeah, in South Africa, Algeria, and Congo, with very different sun irradiation, yeah. And what is very interesting here is that actually in Congo, even though we have all over the year a high radiation, but due to the tropical weather conditions and due to the high ambient temperature, it will be actually the location that need more PV panels and more batteries. So you see here, for a refrigerator cooling down 10 liter of water from 30 degrees to 4 degrees, if you install it in Congo, then you will have to have here 170 watt peak and 2 kilowatt hour battery capacity. And the same refrigerator doing exactly the same with the same user satisfaction will have in South Africa only 120 watt peak and exactly the half of the battery, 1 kilowatt hour. And this is very interesting because this represent also here around 400 euros. So depending where your customer are and for which location you want to design, you will have a totally different design. And now we have finalized the part of solar refrigerators, and I would like to give you an overview how to use now a refrigerator to have productive use, for example, doing ice blocks. So let's have a look how to convert a refrigerator into an ice maker. Here a couple of pictures. It's the same refrigerator I have been showing you the same time, but now it's working as a freezer, so to say. And we have here a fan, which is very important for the heat transfer, because we want to produce ice and we want to produce ice quite fast. We don't have to wait there 2 days until the ice is formed. So we use here a fan, and we can accumulate here 50 kilogram ice, and around, for this case, we will have a look later, but around 16 kilogram ice per day is produced. So you see the same refrigerator, but used in a different way for productive use. And before we continue, let's have a look here to the freezing behavior and to the energy consumption. And this is done now for different ambient temperatures. We start here with 20 degrees. So you see the water first needs to cool down to 0 degrees, and then it stays there until it's totally frozen. So to freeze ice, remember always it needs a lot of energy. To freeze 1 kilogram ice requires the same energy than cooling down 1 liter of water from 80 degrees to 0 degrees. So it is a lot of energy that is consumed to freeze ice, which is also good because then you can use this ice, for example, for fish cooling, delivering a lot of energy. Okay, and the energy consumption you see here, yeah, up to 600 watt hour after 16 hours is what is taken to freeze, in this case 6 liter of water from 20 degrees to -10, and in 30 degrees you see same freezing behavior and more consumption, and of course at 40 degrees we are achieving the maximum power of the refrigerator. That's why the freezing curve is happening a little bit slower. Okay. In the case of an ice maker, the design options are different, like in the refrigerator, because here, for example, we don't need to satisfy an user overnight, for example. We don't need to keep anything cold overnight. We are just producing ice. And once the ice maker is not working because no solar energy is available, or yeah, we are at night, then the ice is kept in the ice maker inside. So the ice itself is serving us as a thermal storage that could actually make the role of the batteries. So here, if we make the decision not to use batteries, this is technically possible, as in the diagram you are seeing here. So you see here the power, PV power available, and the compressor consumption. So here the ice maker is directly connected to PV panels. If it's a direct drive ice maker or refrigerator, you can do it directly. If not, you just need to use a DC-DC converter, and this is working without any problem. As soon as you get a cloud or it's getting dark, then the compressor is not going to be able to work. So you will have the ice maker producing ice for around 7 to 8 hours, depending on the location. You see also you have a surplus of energy that you cannot use because the maximum power of the compressor is limited, and everything that is going above this you cannot use or store. But this is possible. You have a small amount of ice that you produce because you only work 4 hours, 8 hours per day, more or less, as I mentioned. But if the ice maker is not so expensive and you save also a lot of money by the batteries, this would be an option. The other option is to say, no, my refrigerator, my ice maker costs a lot of money, so I want to use it over the 24 hours per day. This is very important because I want to produce as much as ice as possible every day. So then you will have big batteries that are able to save the surplus energy, and the compressor is working at full power 24 hours per day. So you are seeing the first strategy is to say no batteries at all, and here is to say, okay, big batteries to make my ice maker work every day at full power to make the maximum amount of ice per day. But as you can imagine, there is also a way in the middle that is normally the best one, and is to say, okay, hold on, it makes sense to use small batteries because we can save the surplus energy that we have over the day. We can save it and use it at the beginning of the night, and then we can always use the compressor as at a low power mode just to conserve the ice. And then I will say this is a way of using the energy in a better way, in a more efficient way. And let's have a look how this works. We have integrated in the refrigerator a special control unit that is able to decide how much energy is invested in the ice. So if it's sunny, it's investing more energy, or the compressor is working, and at night is taking other decisions based on the battery state of charge. Let's have a look how this works exactly. You can see here the solar power. Yeah, we'll say, for example, the PV power that you have available during a day. And here in blue you see the ice maker power, so the power consumption. So the adaptive control unit is commanding the compressor to work at a maximum speed at minus 20 degrees. So this is then the maximum power mode. So the adaptive control unit realizes, okay, it is sunny, the batteries are charged, let's go to the maximum power. Once the batteries are going a little bit down with the voltage, it means they are not being charged anymore. So they are full, but they are not being charged at the moment. There is no solar radiation. And then the adaptive control unit commands the compressor to work at a lower speed. This means the compressor is working efficiently. And what is also very interesting, the temperatures are also getting down. So we can produce here around 30% more ice during the evening. And this energy is for free because this is an energy that couldn't have been used if we wouldn't have batteries. So this energy, you don't need to increase the PV panels or whatever. This energy you can use because you have small batteries. Once the batteries are empty, we say no problem. We just keep the temperature of the ice maker at perhaps 0 degrees to keep the ice, what is inside, but not to actively produce ice. Yeah, and then this is then repeating. Here will be the efficient mode at minus 10 degrees, and here the sleep mode when we just want to keep the ice at 0 degrees. And this is repeating every day, and it's, so to say, adapting to the weather conditions. So if we have less solar energy available, then we will produce less ice, and in another day that we have more solar energy available, we will produce more ice. And this is balancing because in the ice maker we have a great amount of ice, and if we are producing one day more than the other, it will compensate. So it's a great also thermal storage, and therefore the ice makers, solar ice maker, a great product for productive use. Now let's try to design this ice maker. It is done a little bit different than in the case of the solar refrigerator. You remember with the solar refrigerator we said we want to keep the user satisfied to cool down 10-liter water per day or whatever we decided. And here is different. Here we say, okay, the ice maker should produce as much ice as possible every day, depending on sunny conditions or rainy conditions, but it should try to make the maximum amount of ice every day. And therefore the design is different because if you do a simulation of this for different scenarios or of PV power and battery capacity, so you see here the battery capacity increasing, and here the PV power in watt peak, so more or less PV panels, and you see this is very interesting. If you have, so to say, less PV power, so you see you produce 6 kilogram ice per day only. Yeah, it doesn't matter how much battery you have, because you receive so less energy from the sun because you don't have so many PV panels that you cannot store this energy, you cannot produce ice. Then you see if you go here for 300 watt peak, you go to 8 kilograms ice per day. 350, you go here already to 10. And then you see already an influence of the battery. So let's say if we go to 400 watt peak, and it's very, very small battery, or let's say no battery at all, you will be probably around 8 to 9 kilogram ice per day. If you have a small battery, you go to 10 kilogram, and then you see how much ice you can produce if you have a bigger battery. So you have here 12, 14, 15 kilogram, yeah. And then if you install more PV, then you increase also a little bit the amount of ice, but you see it doesn't react anymore because probably the ice maker here is already working 24 hours. So if you have more PV, yeah, the power of the ice maker is also limited, so then it's, so to say, saturated. And this is very interesting because if you put in relationship or you make the ratio between the amount of ice that you can produce per day and the cost related to your PV panels and to your batteries, then you get a very interesting graph here, and it's the specific cost. So how much euros I pay per kilogram ice that I produce. And you see here, because the ice maker cost is a fixed cost and the battery and PV panels cost is variable. You see we have an economical optimum here in this region, so when we produce a lot of ice. I think this is clear for everybody. So at this range, so when we produce around 16 kilogram ice per day, we are paying 15 euro cent per kilogram ice. Of course, here we are considering a 13 amortization time. That will change also this price, but it's just for you to compare. So it wouldn't worth here to say, okay, I have less PV, then you will pay half, double of the price for your kilogram ice, or here to say I don't use batteries at all, then you will pay around 25 cents per kilogram of ice. So you say it compensates, but it is cost efficient to use batteries. Yeah, you see with batteries you pay less per kilogram ice, but without batteries it is also not so expensive. So it will be around 25 euro cent per kilogram hour. So it depends on your preferences, and of course this will change if the price of batteries, PV panels or ice makers change, then you will get another graph here. But this is the way how to design a productive use system, and here especially for an ice maker. Let's have a look. Now we have decided, okay, to take this combination of around 500 watt peak and the battery is 60 ampere hours, and we can now simulate again for different locations and see, okay, what is going to happen when the weather is changing. So I think this diagram is also very interesting. You see here the daily horizontal irradiation, so how sunny it is. So from 0 to 8 kilowatt hour per day and per square meter. And here you see the daily mean ambient temperature of the location. So what can we see here? You see a lot of points of different colors. So in red will be the weather conditions in Tunisia. In blue, you see it in Kenya, in a location in Kenya, and in green, you see in Colombia. And I have selected these three because they are also very different from each other. And you can see, for example, in Kenya, you see almost all days of the year are between 14 kilogram and 18 kilograms, so around 16 kilograms. So almost every day you are producing 16 kilogram per day, and you can see here is very interesting. When the days are colder, then or so to say, when the days are less sunny, yeah, you go here from 7 to 3, then the temperature is also lower, and the influence on the daily ice production is also minimal. So this is very interesting, and this is because of the fact that when the temperature is lower, you have a better COP, a better efficiency, less thermal losses. So you see solar cooling systems compensate quite well, because normally when it's not sunny it's colder, but this doesn't happen everywhere. For example, in Colombia, where it is quite high in the center of the country, and the altitude is also high, you don't see a difference on the temperature when the weather is not so sunny. So here you are actually going down to 10, 8, 6, even 2 kilogram ice per day. So this location will produce at the end of the day or over the whole year less ice than in Kenya. And in Tunisia you have even higher fluctuations. So you have days which is very sunny and very hot with 12 kilogram ice per day, and other days where you are here in winter also, yeah, by 10 and even 2 kilogram ice per day, even though it is very cold, but the solar radiation is also very low. And here you can have a great overview what is going to happen in your location, and you can then tell your users, okay, this is what you expect. You will have so many days with 60 kilogram ice per day. You will have uh, an average of 5 or 2 weeks of less than 8 kilogram ice per day, and this way you have the design of your ice maker under control. And now we are ready to have a look to also a very interesting product, and this is a refrigerator here also that is especially designed for solar applications and is designed to work without battery. So it's a battery-free refrigerator that you might find also as direct drive refrigerator depending on the manufacturer. And in this case, you just need PV panels, a cable, you connect it directly to the refrigerator. And I'm going to show you a couple of pictures of how it looks like. Here you see it, I mean, from outside, inside, or from the back, it looks like a normal refrigerator. So you don't see here any difference. You see here the condenser and the evaporator. We don't know where it is, but let's have a look inside. You see here the wall. So we were analyzing this refrigerator at our facilities, at our climate chamber, and I will like to give you an overview how it looks like inside. Look here, the evaporator is not like just in the wall. It has an ice storage or a thermal storage. So you can see here the pipes. This is in the back wall of the refrigerator. They are going here like this, and you can see here these bags. This is like a phase change material. So it's a kind of paraffin. We don't know exactly what this manufacturer used, but you can imagine these ice packs are freezing during the day. So when the solar energy is available, the refrigerator is producing here ice, and overnight the cold energy is coming from these ice packs. So the evaporator is covered by ice packs so that it has an integrated thermal storage. And this is very interesting because you can keep the temperature in the refrigerator stable even for a long time, and even though you don't have any power input, so to say. Here I would like to show you a test we have done in the climate chamber. We have been simulating the solar radiation of a typical day in Kenya, and here you see the ambient temperature. So it's a day with between 30 degrees maximum and 25 degrees minimum, so quite a hot day. And the solar radiation, yeah, is a typical sunny day also. Here you can see the energy consumption of the compressor. We are around 50 watts. So the compressor is of course only able to work when solar radiation is there, but not always, right? At the very beginning of the morning, the compressor doesn't have enough power to start. It tries once and again to start, but then it realizes I don't have enough power to start. So it has to wait until the solar radiation has enough power to let the compressor start, and this happens normally around 2 hours after the sunrise. Okay, and then the same happen in the evening, and here I can tell you we have around 8 hours of operation of the compressor. In these 8 hours, the refrigerator is producing ice in the thermal storage, and let's have a look what is happening with the temperatures, right? So once you start the refrigerator, the temperature in the inner chamber goes down in the first day. You see here we are around now 13 degrees. You see here 3 curves in the top, in the middle, and in the bottom of the refrigerator, because we have 13 stratification of temperature, especially in this high refrigerator. So I wanted to show you the 3 temperatures. And then overnight, the temperature is going again up, right? Because it hasn't produced so much ice storage. So these kind of refrigerators take 1 up to 2 days until the ice storage or the thermal storage is loaded, so to say. Yeah, it is like in a conventional PV system with batteries. You need, if you have empty batteries, you need a while until you charge them, right? But here is the same. But in the second day, you see, it goes down during the day to maximum of 12 degrees and here a minimum of 7, so between 7 and 12 degrees, and it stays stable over the whole night, only coming from the thermal storage. And then on the next day, we cool down again and it remains stable. So you see here how nice a battery-free refrigerator can keep the temperatures stable without the use of electrical batteries. But I think now everybody is having the question, okay, what's happened if I open the door, if I put something inside? So we did that also, of course, and you can see it here. So the refrigerator was already fully charged. The thermal storage was charged, so we let the refrigerator work for a couple of days, and then in the middle of the night we put it 4 kilogram food, which was actually water at ambient temperature. So here at this case at 27 degrees, I will say. And then you can see even though the compressor was not working, the refrigerator was able to cool down this water down to 17 degrees. And then the compressor started, the water was keep on cooling down. And then you see even on the next night, the water was cooling down. So the thermal storage was reacting well. And then the temperature was stable here at around 12 degrees. So you can see here how the refrigerator is reacting well. It's cooling down this amount of food, which I will say, it could be the amount of food that you insert into a refrigerator in a normal household, and it is actually the maximum, I will say, that you will enter. So here we could test that the performance of the refrigerator was well, and also here the temperatures, the air temperatures. So you see they were of course affected by entering the food. This happened also at home. Once you enter a warm food into the refrigerator, the air temperature goes high, but it was kept stable. So I will say for the remaining food in the refrigerator, this is not affecting so much. So you see they are very interesting. You save a lot of money in the batteries, but you cannot use it to cool down 10 liters of drinks per day or 20 liters of drink per day, because the compressor is at the end of the day only working 8 hours per day, and this limits a lot the performance, not the performance, but the cooling power, so to say. So a great technology for household applications, but not for productive use, as you saw before, where it makes sense to use batteries. Okay, and that's all. You got an overview of solar refrigerators and how to design the PV panels and the batteries. We went also through how to convert a refrigerator into an ice maker and which considerations we need to take, as the use of a fan, an adaptive control unit, and small batteries to have a economical optimum of the design of the system. And at latest, we had a look to the battery-free refrigerators and their performance. We came to the end. I hope you enjoyed the lecture. Let me know if you have any open questions. And I thank you a lot for your attention. Bye bye.